So please let me take you to this journey to the center of the Earth through my experience with Borexino and GeoNeutrino analysis. So along the journey to study the interior of the Earth, we really encountered many beasts that we had to fight, as Jules Verne described in his story. And I would like to bring you hints of how about the analysis itself, of course, putting it in the framework and some introduction, both concerning like the definition of geoneutrinos, the Earth, and why geoneutrinos can be or are an important new tool to study the Earth. Of course, for young students who might be connected, I will also describe a little bit about the neutrinos' basic properties. I will introduce the Borexino experiment, in which I work since like for 15 years. And then I will speak about this geoneutrino analysis, latest results, and geological interpretation of this. So I think each of us and mankind as such has witnessed a lot of spectacular processes living on the surface of the Earth. It can be destructive, as we can see on this picture on the left. This is a really terrible earthquake which happened not so far from Borexino side in L'Aquila, and local people really suffered a lot. Sometimes it can be spectacular and observed from a safe distance. For example, this upper plot, it's the eruption of volcano which I photographed on an expedition to Kamchatka. Or we can just admire on the surface of the Earth the previous layers deposited on the floors of the faraway oceans. So we might ask, from where is coming the energy driving these processes? And in particular, as now as neutrino physicist, I pose the question, how can this neutrino physics help us to understand the energetics and the interior of the Earth? So let's do the simple definition of geoneutrinos. Geoneutrinos are electron flavor, typically antineutrinos, which comes from the decay of long-lived radioactive isotopes naturally present in the Earth. But long-lived means they have the lifetime at the range of the age of the Earth, which means they did not decay away. So we can also see that the amount of antineutrinos and the amount of the so-called radiogenic heat is well known and fixed. The most abundant isotopes contributing to the antineutrino or geoneutrino flux is a chain of uranium-238, of thorium-232, and the decay of potassium-40. These antineutrinos are a unique direct probe of the deep Earth, because these geoneutrinos, as they decay, come to us and we eventually can detect them. In spite of the fact that the radiogenic heat and the number of emitted antineutrinos is fixed in practice, from the measured geoneutrino flux is not so straightforward to extract the radiogenic heat as always, and I will try to explain this in more detail. Nevertheless, Earth shines in geoneutrinos with the flux of about millions of geoneutrinos per centimeter square through your fingertip. This seems huge, but actually it's the event rates are still small, and comparing, for example, to the solar neutrino flux from the sun, which is far, far away with respect to what we have underneath, this is 4 orders of magnitude less. So let's have a look a bit of to our past. The Earth was created in the process of accretion from small objects, and as the size was growing, the temperature inside was growing as well, up to the point that the metallic core segregated as the first from the silicate, so-called primitive mantle, which was a magmatic ocean, and only later on from this magmatic primitive mantle differentiated the present-day mantle and crust. To study the interior of the Earth, one can pose many questions about the composition of the mechanical layers or about the dynamic of the Earth. I will now try to give you a little bit quick overview of different properties, focus on what is important for geoneutrinos. So the interior of the Earth is composed from the inner core, which is solid due to the pressure of the upper layers, and it's an alloy of iron and nickel. The outer core, the other yellow, is still iron-nickel alloy with some admixture of lighter elements. We don't know actually what is that, and we know that it's liquid. And the movement of this metal in the residual field of the sun's magnetic field, it has an important role in the process of generation of the Earth's magnetic field, so-called geodynamo. The metallic core is divided from the silicate part of the Earth through the so-called D double prime layer, which is a core mantle transition of about 200 kilometers thickness, the strong seismic discontinuity, and we don't know so much about it actually. And then comes the huge amount of this red region, which is lower mantle, which is actually the focus of geoneutrino study that I will explain better shortly. From this lower mantle, we don't have direct rock samples. This material is, we know that it's solid, it's not melted, it's not magma ocean, but it's viscous on long time scale, and there is ongoing convection. This we know. We have proof that the lithospheric tectonic plates, which are driven by this convection and they move few centimeters per year, that this movement is ongoing. But we actually don't know if this convection is remixing the composition of the ore mantle, or there is stratification, which would have also consequences possibly on the distribution of uranium and thorium in the mantle. So, and we don't know much about the composition of it concerning the uranium and thorium abundances. The upper layers of the mantle are also more complicated than from the structural point of view. There is the transition zone. It's again a seismic discontinuity from which are melted out in the process of partial melting. For example, along the mid-ocean ridges, the oceanic basalts, which are creating the oceanic crust. The uppermost mantle is chemically not so much different, but it's characterized by brittle deformation. So, and together with the crust that upper mantle belongs to the lithosphere, which is a unit which is then floating on this more plastic lower mantle. The crust itself can be divided in two categories. Along this mid-ocean ridges is creating the oceanic crust, which is relatively simple, only about 8 to 10 kilometers thick, and it's relatively easy to get the information about its composition and structure. What is much more complicated is continental crust, on which the Borexino is actually placed, and is typically about 30 kilometers thick, but can reach up to 70 kilometers thickness for example, in the region of Himalaya, where it is more or less doubled in thickness. It is very heterogeneous in composition. There can be igneous, metamorphic, sedimentary rocks, and so on. So to estimate the composition and the contribution of uranium and thorium is not always straightforward. We learn about the deep Earth via seismology, which studies the propagation of the S and P waves generated during the earthquakes. From that, for example, we know that outer core does not allow the S waves to penetrate, so we know like this that it's liquid. Geophysicists make the profiles of the density, which indirectly gives hints on the composition. But direct study of the composition of the Earth is the subject for geochemistry. Of course, very precious are direct rock samples, but the deepest borehole is about 12 kilometers, which is, even comparing to the thickness of continental crust, a small number. We have some samples from the upper mantle brought to the surface by different tectonical processes or volcanism, But from the deep mantle, we just don't have the samples. And for the rest, geochemists have to rely on geochemical modeling. And like that, we come to the concept of the bulk silicate earth models. So in practice, these are the models which predict or model the composition of this magmatic ocean, of this primitive mantle, of this today, if we would remix in roughly said present day crust and mantle. What helps here is, for example, the correlation, as we see on this plot, that we see in the composition of the sun and of the so-called C1 carbonaceous chondrites. This is the relative abundance of elements relative to silicon, and you see it's perfectly correlated. So one can say, like simply speaking, that, okay, why the Earth, which was created in the space somewhere between sun and the material which is now characterized by chondrites, why it should be different. Plus that you have boundary conditions of the composition of today, present day rocks and so on. So these models are complicated. There are many inputs. And they predict the abundances of all elements, and in particular for us of uranium, thorium, and potassium in the primitive mantle. So in principle, if you can subtract the amount which is relatively easily of these elements observed, let's say, in crust and continental lithospheric mantle, from which we have samples and it's easier accessible. If you subtract this observed lithospheric part from the prediction of the bulk silicate earth models, you get the amount which is expected in the mantle. And while this known amount of uranium, thorium, and potassium, which can be transferred to the amount of radiogenic heat, which is 7 to 9 terawatt, what remains, according to this simple subtraction for the mantle, spans from 1 to 27 terawatt. So you see that there can be almost nothing or much more than in the lithosphere. And this is what geoneutrino studies should pinpoint. Let's have a look a little bit about the distribution of uranium and thorium in the Earth. In this plot, we can see the temperature of the condensation from on the x-axis and the normalized abundance of these elements. And why it is important, because during how the Earth was cooling down, the elements which are so-called volatile, so they have low condensation temperature, could easier escape. While these refractory elements, especially as uranium and thorium, they are expected to remain in the Earth in unaltered ratio. Therefore, in geoneutrino studies, we believe to be allowed to fix uranium and thorium ratio in the geoneutrino analysis to the ratio as observed in meteorites. Potassium is a little bit different. It's on the halfway between refractory and volatiles, and some part could escape. In addition, these elements are so-called lithophiles. So they like rocks, they don't like metals. So we don't expect them to be in the metallic core, only in the mantle and the crust. And in addition, in the process of partial melting, these elements are always concentrated in the fluid melted out liquid, which is lighter in density, and therefore tends to go up. So therefore, it's continental crust, which is the most differentiated structure, has the most of uranium and thorium concentration. As we can see in this table, the uranium concentration is just going down, going deeper, and in the mantle it's about 3 orders of magnitude less than in the upper crust. Then how this uranium and thorium is distributed in the mantle, we just don't know. So when we do this simple calculation of BEC model minus lithosphere, you are left with abundances in the mantle, and we construct the models just as the extremes, that if you distribute homogeneously, that it would be homogenized by the convection, you get the highest signal. If you intermediate model is if you would have 2 separate convections in the upper and lower mantle, and the lowest signal would be that you have all uranium, thorium squeezed as the core mantle boundary. What about the heat flow? There are thousands of drill holes unevenly distributed on the Earth's surface, along which are measured the temperature gradient, from which one can model the heat flux. When you, there is a lot of systematics connected to this, especially because we are missing samples along the mid-ocean ridges and in the hot regions where there is a lot of heat going out, a lot of fluid circulating, taking away heat and such. In spite of that, geophysicists quite converge on this number that the integrated flux around the Earth is 47 plus minus 2 terawatt. Now, about half of this amount is expected to be from the latent heat from the time of accretion of the Earth. Core is cooling, mantle is cooling, and the binding energy, finally, of this original object is still being released from the Earth. The other half, more or less, let's say, is the radiogenic heat. And that's where the GeoNeutrinos should help. Especially concerning the mantle radiogenic heat, as I explained before. So to summarize, while it is straightforward through nuclear physics to connect the abundances of uranium, thorium, and potassium with the radiogenic heat, we need inputs from geologists about the distribution of radioactive elements inside the Earth to both predict the GeoNeutrino flux and from the GeoNeutrino flux, which is measured, to extract information about the radiogenic heat. So neutrino geoscience is truly an interdisciplinary field of when the know-how and terminology of two groups really has to evolve and we have to work together. So the main goal is this mantle radiogenic heat, but there are further goals. For example, one can study if this uranium and thorium ratio, the bulk ratio of the Earth is actually really the same as we expect in as we observe in chondritic meteorites. One can study if mantle is homogeneous, if there is any stratification, or even to pose limits on exotic models, as is, for example, uranium-based georeactor in the core of the Earth. So now let's have a look at the expected signal. So this is the model and calculation. On the top, actually, this is based on also quite sampling about the CRUST, which is the easier part. You can see that the hottest signal from GeoNeutrinos comes from the Himalaya region. But even in this hottest part, the scale ends at 50 TNU. TNU, it means terrestrial neutrino unit, which actually means that 1 TNU is one event per year in about 1 kiloton liquid scintillator detector, so it's no plus, with a detector of 100% detection efficiency. So, I mean, in 1 year, 50 is maximum you can get from the CRUST. So the numbers are small. What gets even more scary is if you look at the mantle, and this is one exercise of the calculation for one particular BSC model in case there would be that the composition of uranium and thorium would be following the inhomogeneities in the speed of shear waves. There are such anomalies below Pacific and Africa. And one possibility would be that there would be hotspot in GeoNeutrino flux under Africa, which would be then about 10, 11 TNO. So really 10 events per year for 1 kiloton detector. This is really impressive experimental effort to really get high statistic significance information about the Earth, but we still believe that it's possible. So now quickly about neutrinos for young students if they are connected. Neutrinos are really special. They don't have any charge. They interact only with weak forces, what makes them really difficult to detect. We need large detectors, underground laboratories to shield against cosmic radiation, and extreme radio purity of the materials. To detect 10 events per year from the mantle, you have to really suppress a lot of radio impurities. On the other hand, this property of neutrinos is enabling that they bring really unperturbed information from the source. As in our case, we are interested from the depths of the Earth. In neutrino physics, today there are still many open questions about the origin of the mass, whether there can be CP violation in this sector, about normal or versus inverted mass hierarchy, existence of sterile neutrinos. Just to demonstrate, it's really vivid active field also from the point of view of physics itself, basic elementary physics. You certainly know about neutrino oscillations. The important part for geoneutrinos is that this process, which is based on the fact that flavor eigenstate and mass eigenstates differ, and they are connected through this mixing matrix parameterized by 3 mixing angles. And the neutrino have non-zero masses, as it was actually confirmed by or discovered by observation of the process of neutrino oscillation. But actually in practice means that the geoneutrino, for example of geoneutrinos, which is born with electron flavor, has a non-zero probability that after some distance it has percourse, the baseline, it can have a probability that this electron flavor change to another flavor. And this is very important, especially in detection of geoneutrinos, because the detection interaction is only sensitive to the electron flavor, its charge current interaction, and I will show in detail later on. There are many sources of neutrinos, both natural and today even man-made, which span through the many orders of magnitude of energy. And geoneutrinos are typically few MeV antineutrinos. So now let's come to the experimental part. Only 2 experiments today succeeded in detecting geoneutrinos. It's CAMLON in Japan and Borexino in Gran Sasso in Italy. They are both large volume detectors. They have high radio purity, and they are both in underground, placed in the underground laboratories. The geological setting is different. Borexino is on continental crust. The CAMLON is on the margin of oceanic and continental crust, and different geological settings far away from each other makes them also beautifully complementary concerning the comparison of the signals that they observe and testing, for example, the strength of the signal from the mantle. CAMLON was originally built to detect reactor antineutrinos, so it was not posing such extreme requirements on the radio purity of liquid scintillator, which was the case for the Borexino detector, which aims at primarily was constructed to measure singles from the elastic scattering of solar neutrinos. Also, since CAMLON was constructed to measure reactor antineutrinos, originally this background for measurement of geoneutrinos was very dominant. In Italy, there are no reactor antineutrinos, so reactor background is not such a huge problem. Of course, they are. The closest reactor is about 400 kilometers from Slovenia. After Fukushima disaster in CAMLON in Japan, however, many reactors were switched off and they have beautiful data with much less antineutrino background. CAMLON is also about 3 times bigger, so has much higher statistics. On the other hand, is a little bit shallower, so has a little bit more cosmogenic background. So here is a little bit overview of all the published results of geoneutrinos. CAMLON started this study is in 2005 by publishing in Nature the first investigation when the statistical significance was below 2 sigma. Then both experiments started to improve the statistical significance and the precision. And currently, both experiments reached about the same precision of about 15-16 CAMLON, 17 to 18% Borexino, while Borexino reached this precision with about 7 times smaller statistics, and is dominated by really statistical error. So let's go now to details to Borexino results. Borexino is a collaboration of about 100 scientists from Italy, Germany, Russia, France, USA, and Poland in alphabetical order. It's placed in Gran Sasso underground lab in central Italy. There is a highway going from Rome to the other side of Italy. And under the Gran Sasso mountain, there is deviation where you enter to the world's largest underground lab. And in one of the halls, the Borexino detector. About 300 tons of liquid scintillator, which is the world's radio purest. The levels of radio purity is really spectacular. There are about 2,000 nominal PMTs observing the scintillation light, which brings us to about 5% energy resolution at 1 MeV with 500 detected hits per MeV. What is important for our detector that this pseudocumen has an excellent capability to distinguish alphas and betas, which is important also in case of geoneutrino analysis. Around the core of scintillator, which is contained in a thin so-called inner vessel balloon, there is a buffer region which shields the scintillator volume. All of that is inside a stainless steel sphere on which are actually mounted the PMTs, and all is then surrounded by the water tank, which serves as a shield against neutron and gammas from outside, and also as an active muon veto, particularly important for geoneutrinos. Here is a photograph of the interior of the field detector just after filling many years ago. You can see the PMTs and the central inner vessel, which is then anchored here on the south and north pole. Borexino performed a few years after starting of the data taking an extensive calibration campaign with gammas, and particularly important for geoneutrinos, also americium beryllium neutron source. Of course, there was also external calibration, laser calibration with of PMTs in charge and timing, and all this is very important in order to extract, to tune, to calibrate the Monte Carlo, which is fundamental for all analysis. Of course, it contains the tracking code, electronic simulation, reconstruction code, so-called echidna. The same for Monte Carlo and all data, whether calibration or real data for the, the data for the analysis. And it's really fundamental for all analysis for fits, and especially for studying the systematic errors. Neutrinos are detected by this charge current interaction, so-called inverse beta decay, IBD, where electron flavor antineutrino is captured by free proton, which means hydrogen nucleus, in which is produced positron and neutron. Since neutron is a bit heavier than proton, there is 1.8 MeV kinematic threshold of this interaction. When neutrino has 1.8 MeV, there is no energy left no kinetic energy left for the pull positron. So at the threshold, when antineutrino has 1.8 MeV, the prompt visible signal is 1 MeV of the two annihilation gammas. So the prompt spectrum starts from 1 MeV. Then if there is prompt, there must be delayed, which comes from the neutron, which first has to be thermalized, and then eventually is captured in Borexino in about 250 microseconds on proton, typically, and at that moment emits 2.2 MeV gamma. So by this prompt and delayed signal, one can strongly suppress many backgrounds. So how can one calculate expected geoneutrino signal anywhere, especially in particular in Gran Sasso? One has to have several ingredients. One has to know the distribution of uranium thorium, in particular around the experimental site, because on the continental crust, which is rich in uranium and thorium, you have about half of the signal come from the area of few hundred kilometers. Then, as you go farther, you can do approximations. Other important ingredient is geoneutrino spectra per decay. And here we can see the spectra of antineutrinos from uranium, thorium per decay on one mother element, and in red of potassium. This is the antineutrino, the threshold of the IBD interaction. So you can see that actually we can see only the tails of uranium and thorium spectra. You have to know the cross-section and its energy dependence, of course, for the IBD interaction, which is not a problem. And you have to know the survival probability or the oscillation probability, because IBD is sensitive only for electron flavor. By doing this educated sum through all the voxels in the CRUST, which is then simulated, and doing your assumptions of the MANTLE as I described before, you can extract the spectral shape of uranium and thorium, and also the amplitude, so the final flux of geoneutrinos you expect. And in case of Gran Sasso, this ranges from 28 to 45 TNO. There was also performed a detailed geological study in which I was personally not involved. Also, it's not of Borexino collaboration, but there was definitely a study with geologists really fully involved in the several voxels around Gran Sasso, when there was a 3D mapping of different layers, many sampling, and so on. A little bit more detail about the effect of neutrino oscillations that I already mentioned. For 3MeV antineutrino, the oscillation length is about, so one full cycle of oscillation is about 100 kilometers. So in case of geoneutrinos, which are coming from, let's say, homogeneous source as the Earth of several oscillation lengths, many of them considering the radius of 6,000 kilometers, such that within the precision of the current experiments, we can assume that there is no spectral deformation, and only the overall flux of electron flavor neutrinos is diminished to about 55%. This is, of course, not the case for reactor antineutrinos, which are the same electron flavor antineutrinos and are emitted from nuclear power plants. These are singularities which can come from well-defined baselines. They can be nearby, they can be farther away, but overall, you have to consider this to calculate the spectrum for reactor antineutrinos, summing really individually through all reactors. There are, unfortunately, also non-antineutrino backgrounds, and these were really the beasts along the journey to the center of the Earth to really understand them, even if they are small. But to prove them they are small, it was quite a job. So there is a cosmogenic background related to the cosmic muons. We have about 4,300 muons crossing the scintillator or the buffer region. And they can create two kinds of backgrounds. So there are either fast neutrons, which can penetrate to your detector even from the muons which are not even crossing the detector. There is also nasty lithium and helium cosmogenic background, because they can decay in beta plus neutron, so perfect IBD-like event. So you cannot avoid them. You just have to veto about 2 seconds after the muon, around the muon or around or the whole detector. There are accidental coincidences, so random space and time correlate, randomly falling events close in time and space, which of course depends on the purity of the detector. And there is so-called alpha N reaction, which alpha originates typically from polonium-210, which is the only major alpha emitter in Borexino, which fortunately, due to this alpha-beta discrimination, can be very well on event-by-event basis identified. So we know precisely how much polonium we have. We know the fraction of carbon-13, which is the target of this interaction in the scintillator. And knowing the cross-section, you can very well constrain this alpha and background. So knowing the backgrounds, you have to, and your signals, you can tune your cuts. In principle, you have to select the charge cuts, depending you have to be for prompt above the IBD threshold. You want to select the gamma peak of 2 MeV, allowing for some low energy tails due to the spill out effects at the border. And in this analysis, we also added a 5 MeV line from the about 1% cases from the capture on carbon-12. You have to then do the time and space correlation. In this analysis, we looked also in the events which are closely coming one after another within one data acquisition gate of 16 microseconds. And we also increased a little bit the correlation, the DR cut from 1 to 1.3 meter to increase the efficiency. We also developed a complicated veto for different categories of muons. I'm not going to discuss the details, but finally from the average loss of 11% when we've been doing 2-second cuts after each muon, we decreased the exposure loss only to 2.2%. We also improved the so-called dynamical fiducial volume cut, which is cut on the minimal distance from this balloon holding the scintillator, because this is the source of radioactivity as well eventually. But in particular, we don't know its shape. There is a small, there is a small leak which causes the vessel to deform, and we have to reconstruct it based on the events coming from the radioactivity on the vessel. And this has some uncertainty. So we had to optimize this cut, and we request at least 10 centimeters distance of both prompt and delayed from this from the vessel. We require that both prompt and delayed is within 2 milliseconds isolated from neutron-like events to avoid that there would be other neutron-like events which have minimal probability to appear randomly. While, for example, if you would not detect the muon, multiple neutrons would has higher chance to occur after muons. So it would be a fake cosmogenic events. And in order to suppress radon-correlated rare decay of polonium to alpha plus gamma, this is only during the special periods we require when there was more radon due to the process of purification of the scintillator, but to include such periods, we can take it, but we add alpha discrimination cut on delay because of this radon-correlated background. In the end, we found 154 IBD candidates in the period from end of 2007 to April 2019, so 3,260 days of data taking. And all this distribution follows the expectations, both the energy spectrum of prompt, the energy spectrum of delayed, so 2.2 MeV gamma with the low energy tail due to the spill out, and 3 events at the region of carbon 11 capture, or capture of neutron on carbon 12, sorry. The distribution of time of these events in time is flat. It follows the expected radial distribution. And we also cross-check that when you plot these events as a distance with respect to the inner vessel, in case this would be a source of some extra background, everything is okay. So now you have your IBD candidates, and they can be due to the GEONEUTRINOS, reactor, or non-antineutrino background. So you have to do your fit to disentangle these components. So you have to do some constraints on the background. For the lithium and helium background, you can do it by observing the lithium candidate within 2 seconds after muons. And then you can make an estimate and constraint how much you have in your exposure, which was not vetoed. For alpha N, you can select the polonium events, you have your Monte Carlo, and you can also do very good estimate of the alpha N background. The same for accidentals by measuring accidentals in the time of flight window. And in total, we estimated to have about 8 events of background within these 154 IBD candidates. These 3 backgrounds, lithium, accidental, and alpha N, we also constrain in the spectral fit based on these estimates. There are also antineutrino backgrounds. We did a very detailed calculation of the expected background from reactors, considering also the different parameterizations of the shape with bump, without bump, but this is included in the systematic error, but has no impact within the statistical error we still have. We have information from the PRIST database in IAEA about the thermal powers of reactors and the monthly load factors. So with the granularity of 1 month to calculate the the flux emitted from each board reactor. And then there was in this work also effort to try to estimate atmospheric neutrino background, which is small, and especially at these energies, there are problems with the simulation, and there is imprecision in simulated atmospheric background, which was estimated to about 50%. And due to the large uncertainties here, we include including atmospheric neutrinos, which the numbers are still very small, including or not including in the fit as a source of systematic error. So let's look at the result. So this is the spectral fit of the 154 prompt IBD candidates. In case in blue, we keep the uranium and thorium ratio fixed as expected based on the chondritic meteorites. We also keep reactor antineutrinos, these yellow ones, the amplitude completely free, absolutely no constraint. And we constrain non-antineutrino background according to the expectations to this very small contribution. This is a contour plot for the number of geoneutrinos. You see the best fit is 52, 53, and non-zero is excluded at 8 sigma. On this axis, we see the number of reactor events, non-constrained, and they are completely in agreement with the expectation calculated within the precision of these bands in condition of with and without the 5 MeV bump. You can see our statistical error is about 9, while the systematic error is 2, 3 events. So we are by large dominated by statistical error. Now, if you know the number of events, you know your efficiency based on your cuts and Monte Carlo, and you know your exposure, you can convert number of events to the terrestrial neutrino units, which is in this case 47 plus minus this 18%. And you can compare it to the predicted flux, I mean the contribution from the crust and from the lithosphere, the local crust and the lithosphere shown by green and brown. And the mental contribution, you can consider different bulk silicators models. We have here different authors of different bulk silicators models. And you can make this intermediate scenario for the distribution of uranium and thorium. And this is the prediction of the possible signals in foreground SASO compared with the measurement. These are the error bars. So you can see our value is on the higher part, but still 1 sigma bands is touching almost for all models. And just for the Javoa model, there is a little bit more than 2 sigma. I would not call exclusion, but the difference is at the level of 2.3 sigma. This is a fit when the uranium and thorium contribution is kept completely free. All the rest is the same. And this is the contour plot of thorium and uranium. This is the chondritic expected ratio. So you see within 1 sigma we are compatible, but all events can be explained either by only thorium or only uranium. So we made then a sensitivity study with the exposure and conditions as is the data of several thousands of toy Monte Carlos, in which we injected the thorium and uranium signal ratio as expected based on the geological studies. And this line, the dashed one is, this dashed line is the distribution of the fit results. So you see there are many fits which are railing with thorium at 0. So simply with this exposure, Borexino does not have any sensitivity to say about uranium and thorium. So we don't comment on it. There is no sensitivity. What is, however, important that the sum of total geoneutrino events is very compatible. It was 54 before when the uranium and thorium was constrained. It's 50 something when it's free. Just in this case, of course, the error is 46 instead of 17 or 18%. Now, exploiting the knowledge about the predicted flux from the lithosphere, you can constrain this in your fit, and you can keep the rest of geoneutrino signal for the mantle. If you do that, we obtain 24 plus minus 10, 11 events converted to about 21 TNAU. And based on the log likelihood ratio method, with many toy Monte Carlo studies in which we did not inject any mantle signal, we estimated that the confidence level is 99%. Of excluding non-signal from the mantle, of course. Now let's have a look what we can tell about the radiogenic heat. It's not straightforward, but let's look at this left plot. So on the x-axis, you have the abundance, or which is directly related to the radiogenic heat from uranium and thorium in the mantle. These blue, green, and red contours represent the different groups of bulk silicate Earth models. You can see when you fix the amount of abundances of uranium and thorium and the radiogenic heat, you define the x-axis. Now, a certain amount of uranium and thorium can produce certain signal, what is on the y-axis from the mantle. This depends on how you assume to distribute your signal in the mantle. I told you about the 3 categories. This defines the spread between these 2 lines. The orange curve represents the absolute extreme, which is for sure not the case, that all the 47 terawatts of the Earth's heat would be produced by radiogenic heat. There would be no latent heat. And then you use this area to convert your signal, your measured mental signal, median plus the 1 sigma, plus minus 1 sigma error, and you convert the 1 sigma interval on the flux from the mantle on the interval of radiogenic heat, which is a huge error. So it's 25 plus minus 10, 11 terawatt. And this does not include potassium. So you can sum up to this mantle uranium and thorium heat what is relatively well known about 8 terawatt from the lithosphere. Then you have to do the assumption on the potassium, which, considering different models, is about 18% contribution in the mantle, and you can convert this mantle uranium and thorium heat to the Borexino estimation concerning different models on the potassium and lithospheric heat, 38 plus minus 13 terawatt, to be compared from 47 of the all heat coming from the Earth. Here it's shown graphically. Here we have the 47 band of the total upper limit of the Earth's heat. And this each bar is for one BSE model, and the last column is for Borexino, the dot and the arrow. Contribution of the heat from the lithosphere in brown, it's constant in all models. Radiogenic heat from the mantle, orange, varies according to different radiogenic bulk silicate Earth models. And blue is the secular cooling, so the latent heat from the times of accretion, which is left to fill up the space in addition to the radiogenic heat to reach 47. So you see the Borexino result is not leaving much space to the latent heat, but we are by far not saying that there is no latent heat. Look at the error. 17%, it's still experimentally, we are very happy with this error, but with this kind of error, we are really compatible with all models. We can also convert this information, which is finally the same, but converting numerically to the convective Urey ratio, comparing different models with respect to the measured the best estimate of Borexino. Now, the last exercise we did is about the GeoReactor. There was the suggestions that inside the Earth, whether directly in the center or the core mantle boundary, there is uranium fission reactor, which would then emit spectra with the energy shapes very similar to nuclear power plants. So in this analysis, you have to constrain the reactor spectra from the normal power plants. And you see in the spectral fit how much extra events with this spectral shape you can have. We have made the exercise to calculate the spectral shape due to the oscillations according to the position at the coordinate boundary below the experiment. On the other side, at the center, it looks very different. But when you actually, because there are many oscillation lengths over that, when you actually consider the resolution of the detector, the spectra are the same. So the limit on the number of events and on the TNU of eventual events coming from the georeactor does not depend on the hypothesis from where it is emitted. What, however, depends there how you convert this number of events to the final power of the reactor. Of course, farther away you assume the reactor is, smaller limit you can place. And for the reactor in the core, we place the limit of 2.4 terawatt at the 95% confidence level. So this brings me to the summary. Borexino provided the new GeoNeutrino measurement with all available data up to April 2019. This is the comparison of evolution from 2010 to the latest results. With optimized selection criteria, improved analysis, and at the end, signal is in agreement with geological predictions with a preference for models predicting high uranium and thorium abundances. Now, MANTLE signal is excluded at 99% confidence level. We estimated the MANTLE radiogenic heat, MANTLE minimal uranium and thorium abundances, and Urey convective ratio. However, we have no sensitivity to thorium and uranium ratio. And with this, really, we hope that we prove that geoneutrinos are an important tool to study the deep Earth, but the new generation of experiments is needed for firm geological conclusions. So what we want is more statistics, multi-site experiments, or experiments at geologically particular locations. Unfortunately, Borexino will stop data taking this year, so no big breakthrough in geoneutrinos coming from Borexino. I hope that CAMLAND will soon publish the results. The latest published one is from 2013, and they have beautiful data after Fukushima. Well, I am also very hopeful that in short time, SNOPLAS will produce beautiful new results from the third side, which will be very exciting. Juno, which is also 20 kiloton liquid scintillator detector under construction, in spite of having a lot of reactor neutrinos, in 1 year can collect about 40 geoneutrinos. So we believe in Juno, they expect 17% precision within 1 year on geoneutrino. So in 1 year, what has been done in 15 years of our data. In Jinping, which is a detector under consideration in the deepest lab, focused on geoneutrinos and solar neutrinos. This would be an interesting measurement on the very thick continental crust, so I personally have really strong doubts how much they could tell about the mantle. And the geoneutrino detector would be the ocean bottom detector, originally called Hano-Hano, which would just elegantly measure the mantle above the oceanic crust. And this would be a really beautiful experiment, which I hope will happen once. So thank you for your attention and for this invitation. And if you have any questions, I'm ready to answer.
All right, thanks so much. I will clap in lieu of
Thank you.
The virtual claps. So we have a little bit of time for questions. I know some people have to run to different obligations. So just raise your hands or pop your questions in the chat or unmute yourself if you see an opportunity. Just to start off, I had a quick question about the spectra that you were showing of your fits with the data on top of it. Yeah, for example, there, so any of these, the blue are the geoneutrinos, but what is the contribution just above them?
This is the total fit.
Oh, okay, so okay, these aren't cumulative. These are,
sorry, it is just, yeah.
And I had another question from the very beginning, which was So what's behind the variation? So the variation in the expected flux from the crust, that's because, you know, there's more crust at some places than others.
Okay.
Like in the Himalaya. But what about the mantle? I saw there was a large amount of variation there.
We don't know actually, right? That was the, so in the mantle, we really don't know. It can be completely homogeneous, but there have been observed this large shear velocity provinces, which are anomalies in the speed of the propagation of these waves. And due to the character of the transition regions of these zones, as far as I understand, they hypothesized that it would be not only the mechanical structure, but also bound to chemical anomalies or the different concentrations of these elements. And this was an exercise. They said, okay, if we take the amount of uranium and thorium that certain bulk silicators models predict in the mantle, and we would follow the gradients as observed by this by these velocities measurements, also for the composition, and with the amount of uranium and thorium we have, this would be the map.
Okay.
Right, okay, but it could be completely homogeneous.
Right. Okay. Yeah. So we don't need the error on that.
Yeah, exactly. So this is really one of n possibilities. Yeah.
Okay. I see a question from Ning Chang.
Yeah, and thanks for the very nice talk. So
thank you.
Maybe you have talked about this before. So could you possibly distinguish these geoneutrinos from the direction of the neutrinos? I guess it's hard for like scintillators.
No.
But what about other experiments?
No, I think that for IBDs on the only double show succeed in measuring on statistical level some directionality, but this is in liquid scintillator, this information is lost. And also the neutron, which originally preserves some directionality as it is created during the Menes scattering, during the thermalization, it's really scattered to so many directions that it's very difficult.
Okay, I see.
So I had another, I was also wondering, there was a lot of news recently about the improvements in, was it the polonium background characterization and that then led to the CNO flux detection?
Yeah.
So does that help you as well?
No. I mean, it's for geoneutrinos, polonium is important because of the alpha N background. So for the CNO, it's important to disentangle the contribution of polonium, which is in equilibrium with the lead-210 in the scintillator, and polonium, which is stripped away from the surface of the vessel. Because if you know the amount of polonium in equilibrium with lead-210, you can set the constraint on bismuth-210, which is in between lead-210 and bismuth-210 is important background for CNL. So this was important for that. But for geoneutrinos, it's really enough to be able, event by event, identify the polonium event. So for example, this is the average polonium rate during the whole data taking, and I mean, measured by this MLP alpha beta discriminator, you can see different cycles of filling, purifications, and sometimes, and then we stopped doing anything and it was decaying, and actually now we have a very little polonium comparing to the initial part. But for this study, it's enough to consider the average because we measure yeah.
Yeah, thanks. I don't see any more questions for now. So Thank you again. It was a really, really nice talk. Oh, wait, Tony put his hand up at the very last minute.
Just did the last. This is kind of a stupid question, but I've always been embarrassed by the fact that we know more about the center of the sun than the center of the earth. And typical detectors that we're talking about here are in the tens to hundreds of millions of dollars. Why are geologists not more ambitious? If you gave $100 million to a geologist and you imagined trying to, I know it's a Jules Verne type thing, but trying to develop a probe that could go at least significantly deeper. I mean, at the edge between the mantle and the crust, the temperatures are 1,000 degrees. Tungsten melts at close to 4,000. I can imagine trying to build something with just enough sensors that you could actually be more ambitious and probe more of the mantle. Why are not people trying to do that? Or maybe they are.
Well, I think they are. I think it's first of all not. I mean, I'm no expert on drilling, so I don't know. But I imagine it's not so easy. And concerning the geoneutrinos, however, even if you would go 100 kilometers, so you go below the crest of Himalaya, it's still, I mean, you have thousands of kilometers of material below.
Yeah, I wasn't thinking of, I was thinking about the ability to collect samples as opposed to trying to detect the neutrinos there. But, I thought you could send, and I wouldn't drill, I would drop it through into a volcano where it could figure its own way down through the, through the liquid.
So you mean like here on the journey? Like this.
It just strikes me for the type of money we're talking, if you're thinking as a geologist, I could maybe get an NSERC grant for $20,000. Well, obviously you can't do that. But if you gave them $100 million, yes, that's exactly the Jules Verne. What could you do for $100 million to really learn?
I would prefer to construct Hano, because then you really, I think, test how much uranium thorium is really very, very deep, where for sure you cannot drill to such depths. Which I don't say if it would be technologically possible to drill deeper, would be certainly interesting, especially for understanding the upper mantle and so on. But I really don't know. I mean, if there is 12 kilometers deepest hole, I don't know. I really don't know. I think that most of these boreholes is driven by searches for oil and so on. So,
sure.
Yeah.
I'm going to hire a summer student to build a Jules Verne machine.
That student get $100 million.
Right, exactly. And who will pay?
They do get $100 million if they can figure out how to do it right.
Well, which is not. I think that really. I mean, I don't know the budget for Hano, but there is many years the problem to finance it, because.
Right, but the strategy has to be different, right? Hano has to have a military application, in which case the cost will be trivial.
Exactly.
All right, it looks like we're truly questions. So yeah, thanks again. This is a really fun talk, and I certainly learned a lot.
Thank you very much for the invitation, and for having the patience up to that. Okay, thank you very much. Bye-bye.